min and max values. All right, so here, let C be in the domain of a function, right? So we say a function is the absolute maximum of something if f of c is greater than, so c, f of c is an absolute maximum. So whatever our function value is an absolute maximum if that value is greater than for all values within the domain of f. So that's for everything, right? It's an absolute minimum if it's less than all values, and then we call something a local min if it's for all values near C. And basically that means, I mean, this is kind of hand wavy, but it's kind of like if you can make some small interval a comma b that contains C, like C is some interval between A and B, and it satisfies this, and it doesn't matter how small this interval is. We call it a local max, and we call something a local min. And so the absolute is the y value, and yeah, so these are, and we call the point, and so the point is the, and so we just say what value that is. So example 1. So let's go through this, right? So let's look at this thing real quick. So here we have a graph of some unknown function, right? And I'm going to use an unknown function first, and then later we're going to show you how to use the derivatives to completely do that. But let's make sure we have the definitions underneath our problems. And so here we have some function f of x. I don't tell you what it is. It's just a mess, right? Use the graph to approximate your answer. So where do the local maxima occur, and what are the local maxima, and what are the local maxima points? And so what are the points? What are the I thank you. I don't go away. And so where are the local maxima? So I'm going to zoom in kind of real close on this, right? I'm going to zoom in real close on this. All right, and so let's see what qualifies for what. And so here, I have an open circle here, so this doesn't really qualify. I can't really say that's anything special. Here, I can say this point right here is a local max. And the reason I can, I'm gonna write it a little bit finer real quick. If I'm this zoomed in, I'm gonna say this is a local max. And the reason is even though I'm choosing a very small interval from like here to here, I mean basically between minus, basically intervals between -5 and -4, right? Whatever this value is, I'm going to say that's a local max. So this point is a local max. And then here, I can say this is a local min. And notice this is, and here I can take the same, I can take a very small chunk again. Here I'm going from -4 to -3, right? And so this is a very small interval. But this point is smaller than all those points. Up here, we can say this again. Here's another local max. Oh, I forgot to write. So this is a local min. So this is a local max. Down here is a local min. Here it gets real kind of flat. And then here it gets a little bit fuzzy. And let me double check what your book defines, right? Let me double check your book's definitions. Because you could say it's, let me see. Extreme value theorem. Oh, I'm just going to go ahead and make an executive decision and say this is a local max. And the reason even though I can't make an open interval which contains this point, it's at the end of this function's domain. And so everything up to that tech it. I won't get too much into it. I'll just go ahead and just safely say that's a local max for now. I'm pretty sure looking through your book, it agrees with that definition. Because I've seen books argue both ways. I'm like, come on, book. Graph of the function. Hold on. Ah, here it is. Absolute. What do you think is 4, though? Oh, nope, your book definitely weighs in on this. It says note. Here, let me make a little note so I can cut. Because I cannot show the book, right? Let me make a little note to cut here. So let's see what your book weighs in, right? So I'm kind of just doing something like example here, right? But here I'm just throwing away everything. But let's see how your book weighs in. This is important to know what your book says because that's what you're going to get tested on, right? All right, so here we've defined this point here to be your absolute max, not a local max because it occurs at an endpoint. That's fine. And so your book does not allow your endpoints to be locals because it is strictly forcing it has to be and in some small interval. Your book near C, elsewhere near C, it's for the smallest for some interval I, right? And it means an open interval. Um, your book doesn't define it in the boxes, but it defines it down here. So notice here when it says for 4, notice that F does not have a local or absolute maximum at 4, right? So it's not allowing the endpoints, and that's good to know. That's super good to know. I mean, technically, if you're in a science class, you'd call that a local max, but in this math class, we're not allowing it. All right, so let's go back to this. Draw another little star. So this is not a local max, not anything, according to your book. Just not. All right, so now we've defined all these points, right? So what's a local max? What's a local min? And so here, let's go ahead and define them. I don't think your book gets really into what is the difference between a local max and a local max point. So go ahead and we'll just go ahead and ignore this part for now. So what are the points? And so here we have roughly at, I would say that's f of 4.7, right? Just roughly f of 4.7. Let's go ahead and make my dot less fine. 4.7 is equal to minus 3.7. So f of minus 4.7 equals minus 3.7. And so that's a local max. Another local max here would be f of minus 1 is equal to 3. And so these are our maxes. These are local maxes. And then we'll have our local mins. So we had a min here at minus, I'd say 3.4 roughly. I didn't give you exact things, so you can't say exactly. And that's what 4.4 minus 4.2. And then here we have another local at 1, and that's going to be 5. So f of 1 equals minus 5 is a local min. So here are local maxes, here and here. Our local mins are here and here. Notice that we'll check our endpoints. So you check all the local min and maxes. So where's our absolute max? Oh, these are max. Hi, I wrote this in the wrong area, didn't I? These are our local maxes. Our local mins are over here. So that was f at 1 was minus 5, and the other one was f at, what did I say? 3.4 minus 3.4 was minus 4.2. think that's what I said. What's the absolute maximum here? Well, the absolute maximum occurs right here, right? That's the highest value for everything in this domain. And that's so the absolute maximum is f of minus 1 equal to 3. That's the absolute maximum. What's the absolute minimum? And the thing is it doesn't have one. In this case, it doesn't have one. And let me explain why. It doesn't have one. So notice here that this endpoint is below this local min, right? And since it's below the local min, if it was solid, if this was a solid point, we would say, oh, there's the absolute max. But it's not solid. We actually cannot achieve this point. And so no matter what number I get within the domain, I can always get a little bit closer and a little bit closer to that. And so we say it doesn't have one per se, since we could always move it closer. But notice here, if I wrote this, if this was my function, not in the get up the side, this could be our absolute max. And if this was solid, this could be our absolute min. So what do we do? So what do we kind of do in order to find our absolute max and mins and everything? So we find our local, let me zoom back in. We find all our local mins and max points, right? And we'll end on this page. Oh, we'll just do 5 pages next time, which would be, yeah, it'll be fine. So we have a local max. So you find all your local max and mins. Then you test your endpoints. If your endpoints are open, and you just look at your endpoints. If your endpoints are higher than any of the local, if it's a greater value than any of your local max, you say that's the absolute max. If not, you just choose your largest local max to be your absolute max. Same thing for your local mins. You look at all your local mins and you test your endpoints. If one of the local mins is lower than that, one of the local mins is lower, you should say that's the absolute. But if your endpoint is lower, you say that is. But sometimes you cannot achieve that. And we'll end on this note. Let's pretend if I just looked at x squared, right? Well, x squared has an absolute minimum, 0, right? But it doesn't have an absolute max, because the more I go over this way, the higher and higher I get. So we say it doesn't have an absolute max. And the same thing if we had like minus x squared, right? Here we have a local min here, our local maximum here, but it doesn't have an absolute minimum. But it has an absolute maximum of 0, right? Oops. And so it's just kind of, you have to get used to vernacular. All right, class is over. Wouldn't there be more than one local max? Yeah, there's more than one local max. There's this one and this one. These are two. Okay. Okay, let me answer your questions. So if you need to go, you can go. Let me answer any questions you guys might have. So at the endpoints at the right is the highest, it'd be the absolute max, but it can't be a local max because it's not within an interval. Correct. So according to your book, because sometimes I teach engineering classes, and then engineering class would say that's the absolute max, right? If I hit the end and that's higher than everything else, that's what it is. But in math, we don't like to say that. And so I want to be very clear what your book defines it. So your endpoints are never local maxes or mins, never. They can be absolute max and mins, but they cannot be local max and mins for the case of this book. Wouldn't 2.6, so the point of 2.6 -2 be a local max? Oh, okay, so right here. Notice right here, so that's what you're talking about, somewhere around here, right? If I zoom in here, at no point does this actually go up. At no point does this, if it tilted down just a little bit, I could call it an absolute max, or I could say this point's an absolute max, but it always slowly still increasing. And so we can't quite define it that way. It's close. It's super close though, right? In fact, if this flatlined a little bit, you can declare it to be both local max and mins. And we'll kind of cross that bridge later when we get there. All right, guys. That's the end of today's lecture. Sorry about this. Let's get started. All right, so let's talk about variance theorem. So right now we're looking at min and max values. And so variance theorem says f has a local min or max at c if f at c prime doesn't exist or f of c prime is 0. So I'll give examples of the following. Um, and so here we just want to set up kind of some stuff for variance theorem. So f of c prime equals to 0, but f does not have a local or maximum at c. One of the things is um, so one of the things that's possible is, let's look at the line, right? So here if we have a line, and I put a point on this line, and I put a point on this line, notice that here the derivative is 0, right? Because the slope here is 0, but I don't have a local maximum because any point on this is no longer above or below every other point, right? It's just not, right? And so here I can have c prime equal to 0. So these are kind of the two exceptions. And here's a second, a local max and min. But here, let's pretend I have sharp points. If I have sharp points, um, and then also another thing here, if we have it open, I think technically your book qualifies this. And so the derivative doesn't exist here, but I can have a local max here because this point, well, the function is defined everywhere, is greater than everything. So this is a local max. Notice here at sharp corners or cusp. So a corner is where it kind of goes like this. A cusp is where it kind of comes into like a point. They're not that, I mean, for you guys, it won't look that much different. So this is a corner and this is a cusp. Derivatives don't exist at the points. But notice that these qualify to be local maxes and mins, okay? And so these are just some of the caveats for the rule. So if f is a function, we define critical numbers of f as the numbers of the domain where the derivative is either 0 or does not exist. Okay, and so that's what the critical numbers are. And so we're going to look at this and we're just going to find out what are all the critical numbers. We're not going to say if they're max or min or whatever. We're just going to say what are the critical numbers. And so remember, critical numbers are in the domain. So they're the x coordinate, or in this case, the t coordinate, right? Because this is a yt plane. And so let's define all the critical ones. So right here at 4, notice that our derivative doesn't exist, right? There is no derivative here. Because, and this is like an infinite, where the function goes up to infinity. But also notice that I guess it's not a critical number here. It'll be very, but is -4 in the domain? And the answer is no, right? Since here I can see it clearly doesn't. So -4 doesn't quite qualify to be a critical number because it has to be a number in the domain, right? In the domain. But notice here at -2, we have a critical number. So I'm going to just write, so state the domain of the function. So let's do the first part of it. Let's state the domain. The domain here is values from -infinity to -4. Notice at -4, I don't have anything in my domain because this doesn't work out, right? And then also notice here at 5, it's not defined, right? Here at 1, it's defined up here, but at 5, it is not defined. So here is from -4 to 5, and from 5 to infinity. And so this is the domain. Okay, so that's the domain. Does anyone see why that is? Any questions on why this is the domain? We can't have this point and we can't have this point. So it's everything but those 2 points. The critical numbers exist in the domain. And so where does the derivative not exist now? Well, the derivative doesn't exist or is 0. So here, my derivative is 0 at -2. So my critical numbers are -2. Here, my derivative doesn't exist because here I have a jump, right? Remember, jumps don't allow for derivatives. And that occurs at 1. And then right here, the derivative doesn't exist. That's a sharp corner at 3. And then here, the derivative doesn't exist, but it's also not in the domain at 5, and everything else looks okay. And so here we have our critical numbers of -2, 1, and 3. And notice that here we can have a local minimum. We have a local maximum up here because we can define an area around it in which this is the highest, right? Here we have a local minimum. And so here are the critical numbers. So the critical numbers is where it's either 0. So either where it gets nice and flat, so like this or like this, right? Or when it's a cusp, or if it doesn't exist. So oh, okay, what's the question? So why is to, could you ask your question one more time? I'm trying to understand. Why is it to 5 and not to 1?
Oh, I think Leo might have answered it already for me.
Oh, okay.
My question was, why does it go for the domain all the way until 5 and not 1? But then he told me that it jumps
Oh
up.
yeah, because here
Yeah.
it exists. So it's just where the function's not defined. Yeah. If Leo got it, thanks. Okay. All right. Any questions on this page? Okay, let's go to page 3 then. So once we defined all that, oops, did I not? Did I never officially state something? I might have never officially stated something. Um, can you explain? Someone wants me to ask, can you explain again whether it's an open circle? Again, whether it's open or a closed circle for figure 3. Oh, for figure 3. So what happens here is if you have an open circle with a closed circle somewhere within the open circle, so like here, right? Like here. So here I have an open circle and a closed circle. So the function is defined here, right? And in fact, it's defined in every interval, in some interval around it. So if I look, as I walk this function, everywhere is defined to be that. Here, let me open up something from the first page real quick. Let me open up the first page real quick, which I do not have on me. First page. Where'd you go? Uh, so here we have it to be defined everywhere above near C. And so this allows it to be values near. And so I have to have values above and below it, right? And so since this is clearly defined, I have values clearly defined below it and clearly defined above it, it's okay. But here I'm not defined at all. And so if I have just an open hole, that doesn't count. But if it is defined and the derivative doesn't exist, that's okay. But it has to be in the domain for it to be a critical number. And I think, could you explain? Oh yeah, so here, so we're looking at the domain here, right? So this is the domain. Where's the function defined? The function is defined everywhere up to -4, but at -4 it's not defined because these both go to infinity, right? And then from 4 to 1, it's defined, and it is defined at 1 because I have a value at 1, and right after 1, I have a value. So it's defined through 1 and all the way up to 5. But at 5, if you ask me what's the function at 5, I can't give you an answer because it's not defined. It's not here and it's not anywhere. So it's not defined right here. So, and then it goes further out. Okay. Okay. Um, and so between these two, right? So between two, so fair if it has. So here's a question: if it does have a local minimum or maximum, it's going to occur at these critical numbers, right? Um, but it doesn't guarantee that a critical number is a local min or max. In fact, I think let me redo this one. I want to redo this one. I want to define it to be this. And let's just say this is x cubed. Notice here at 0, the derivative here, we can clearly define what the derivative is. It is 3x. So if the function is equal to x cubed, let me make this very clear, right? And I think this is better in lots of ways. My derivative of my function is 2x, or 3x squared, sorry. It's 3x squared. And so we have x cubed, and we have the function to be 3x squared, right? This is 0 when, so this is equal to 0 when x is equal to 0. But is that a local min or max for this? Of course not, right? Because it's increasing, it flattens out, but now it goes back to increasing. I think the line example, because the way your book defines it, is C is less than or equal to. And since it's equal to, technically everything along this line is a local min or max. With the way your book define it, this is a more correct way of showing that sometimes critical numbers are not necessarily mins or maxes. Okay. Another way, you could have a corner like this, right? Even though this does not exist, this is a critical number. The derivative doesn't exist because it's a corner, and yet it's increasing and then increasing. So this is neither local min or max as well. There's a lot of little caveats on this one, so I try to show you some of them. But let's just get into some hard crunching. So let's do this. I want to find all the critical numbers for this. Okay, and so what do? The first thing I do is I find its derivative. So critical numbers is where either I want to find where either f, the derivative is either 0. So what am I trying to do? Let me explain what I'm trying to do. Is either equal to 0 or does not exist. So the first step we want to do is we take its derivative to find the critical numbers. All right, so we take its derivative. So here we'll have product rule. And so if I took, so I'm going to let this be f, and this be my g. So if I hold f constant, take g prime, so I'll have x to the 3/5 power. The derivative of this would be -1 plus, we'll take the derivative of this, which would be 3/5 x to the -2/5. And then we'll hold this. And so here's our derivative, just using product rule. All right. Now we want to simplify this. And that takes a second. Let's do that. Yeah, I'll just quickly simplify it. I'm not going to explain all the. So here we take out the negative, and this becomes plus 3/5 4 minus x to the 2/5 power. And then if I do some more algebra, put it together, move things around, I'm going to get 12 8x over. Okay. All right, so we have this. That's right here. So that's our derivative. So what do? We set it equal to 0. So hold on. Let me see, make sure I do this correctly. So we want to find out where 0 or does not exist. So let's start with 0. Let's set this equal to 0. So where would this equal to 0? Well, that's when the top part equals to 0, right? When this equals to 0. When this is 0, all of it's 0. And so this is 0 when x is. So hold on. Let me not skip steps. So this implies that 0 is equal to 12 minus 8x, which implies x is equal to 3/2. Okay. You just solve this for x. You move the 12 over, divide by -8, we get 3/2. So here's one of our critical points. The other question is where does this does not exist? Well, it does not exist when the bottom part equals 0, right? If this equals 0, it does not exist. Where does that occur? Oops. Where does that occur? And that occurs when 5x to the 2/5 power equals to 0. Okay, I can't divide by a 0 here. Shouldn't it be 8x? Isaac, yeah. So what I did here, in order to do this, I did skip a step. So I need to divide this by, x to the 2/3, which makes this a positive x. And then in order to put it together, you put a 5 in. And that 5 comes in here to becomes the 8. So there is a skip step. There is a skip step, sorry. No, you're 100% good. You're 100% good. If I skip a step and you get lost, let me know. I just want to make sure we have plenty of time to go over everything. So here, this is equal to 0. That implies x is equal to 0. And so here are two critical points. Our two critical points here, or critical numbers, right, are at x equals to 2/3 and x equal to 0. So what do? You take its derivative, you simplify it as best you can, you set that equal to 0, and you solve it, and then you ask yourself, is there anywhere it doesn't exist? And where doesn't it exist? Well, it doesn't exist at the bottom part of 0, and that's usually where you'll get the DNEs. Not if it's, and you may not have places where it doesn't exist. And so there we go. So let's do this one. So here we're going to we want to find the absolute max and minimum of the function. And so in order to do this, we want to find, and so to do this, we're going to find the critical points of this, which will give us our local min and maxes, or our potential local min and maxes, right? Because they occur at critical numbers, but it's not guaranteed to be one. And then we check our endpoints. And so that's what we're going to do here. So let me write this out in clear steps. Step 1. So here, step 1, take f prime of x. That's the first one. So f prime of x, and this one's really quite simple. So let's just do it. So it'll be 3x squared minus 6x plus nothing. So that's my derivative. All right. All right, step 2, find critical numbers. So critical numbers. Oh, this is f prime, sorry. So we set 0 equal to this. Notice that since this is polynomial, it exists everywhere. So we're only looking for the zeros here. So we have 0 equals x squared minus 6x. So we have 0 equals 3x of x minus 2. So that implies x is either, so x is equal to 0 or positive 2. So those are our two critical numbers. Let's do step 3. And so let's find out what the value is. So find the values. So we're going to find the values of our critical numbers. And what do I mean by that? It means just plug it in. So we're going to have f of 0. So we plug in f of 0. When we plug in f of 0, what do we get? We get 0 minus 0 plus 1. So this is 1. We'll plug in f of 2. And I get 2 cubed, which is 8, minus 2 cubed, which is 8, minus 3 times 4, so 12, so it'll be minus 4 plus 1, so it'll be minus 3. Okay. Step 5 would be to check, or step 4 would be to check, find the values of endpoints. Of the endpoints. I'm trying to make this as clear as possible what to do. So we're going to check the endpoint. So f of minus a half is an eighth, and f of 4 is 17. Okay. All right, so step 5. Step 5 is step 5 is find the absolute, max, and min. And so when you want to find the absolute max and min of a function for a given, you're going to find all the critical points, and then you're going to test your endpoints. So here we found the critical numbers. We found out what values are. So here the absolute max, here, what's the biggest number we see? The biggest number we see right here is at f at 14. So f at 14, that's our absolute. The absolute max here is 17, and that occurs at f equal to 4. The absolute min is here with a critical number. So the absolute min here is f at 2, and that is at minus 3. So the absolute maximum value is 17, right? So the value here is 17. So 17 is the answer. So I'll just box that. And the absolute minimum value is 3. And these occur. I like just to have this when I'm doing it by hand, just to say this is where it occurs. But when you plug into the computer for values, they'll probably just want 17 is the absolute max value, and 3 is the absolute max, absolute minimum value. Okay. And just for fun, when do we know we also need to find when it does not exist? If you have a rational, it's like 99% of the time, it's if you, when you take a derivative, you get a rational, aka a polynomial, find out where it's 0. Or sometimes you'll have square roots. Just 90% of the time for this book will be something over something. So the absolute doesn't have to be given in the domain of the problem. Yes, this one has to be in the domain of the problem, because 4 is in the domain. And so is 2. Let me show you. Go to Desmos real quick. Let's just Desmos. There we go. Not what I wanted. Desmos. Hey, that's what I wanted. Yes, in this case, let me graph it. It'll be really clear if I graph it. Hi. Minus. Let me show you what I'm doing. I'm just in Desmos. I'm just typing this in. Please type stuff into the graphing calculator. Look at it visually. It's, most of you are visual learners, even though I'm not. You guys are. And is there a way to define where x is minus? Can I type that in somehow? I don't know if I can type that in. We'll try it real quick. Nope. There we go. X. There we go. 4. Nope. Oh. Can I use a comma to say that? No. Oh, screw it. I know an easy way to do this. I'm just going to draw a line at x or at y equals or x equals was it 1/2? Yeah. Or minus 1/2. Sorry, minus 1/2. And then should we make that a different color? No, of course not. Be that way. Oh, perfect. All right, so here's what we're looking at, right? Right here. Okay, so we're looking at between the purple and the black. And so here's our function. It goes up, comes down, and it goes up. And notice here, we have 417. And so it's defined at that point, right? Notice here it is clearly defined at that point. So less than or equal to 4, so we all are there. So this is our absolute maximum value. And by looking at this, we can see that our absolute minimum value occurs at this local minimum, right? Here at this local minimum at 2, -3. And here we have a local maximum of 0, 1. And then here we also have our endpoint of 0 and 1/8, or negative 0.5 and 1/8. Did I not write the negative? No, I did. So does that kind of clear it up? You can type it into Mathway. Oh, well, I'll use Mathway next time. Okay, hopefully that clears it up. Looking at the graph helps. So if you ever get confused what's going on, graph these things. Please, by all means, graph these things since you're going to be doing it on the computer anyways. Okay. All right. So let's do the next page. I think the next page is just, oh, the next page is just for us to get used to things coming soon. Okay. This is kind of a little preview. All right, so once we determine critical numbers of a function, we want to determine the behavior between each of those critical numbers. We do this by creating a sign and an interval. So basically, so the first derivative of this function is given by this. Already defined what the derivative is, right? And so what are the critical numbers here? Well, the critical numbers here are 3 and 1, right? This gives us 3, this gives us 1. We set it equal to 0. And so if we look at this, and so here I have them. I spent a lot of time. So here we have this graph, right? It looks a lot like we just did, right? And here we have our function value, right? Here we have our function value here and here. So this is our derivative, right? This is our derivative in blue and our actual function in purple. And so we're going to look at intervals around the critical points. And so we're going to go from minus infinity to 1. And then we're going to go from 1 to 3. And then we're going to go from 3 to infinity. So we're going to look at intervals of our critical points. Now, what's the sign here? Well, here the sign. Let's do it here. Let's just choose a point of 0. If I plug in 0 here, I'm going to have 6 times -3 times -1. And so that's going to be positive, right? And notice here, that matches what we see here. We have positive values. If I'm going to choose a number between 1 and 2, let's go ahead and plug in 2, right? I'm just choosing something just to determine the sign. And so here I'll have a positive, or a negative, because 2 minus 3 would be negative, plus something would be a positive. And so this would be negative, because I'm positive, negative, positive. And then here, if I choose, I don't know, 5, it's positive, positive, positive. So this is positive. Notice here, that matches what we have here. We have f to be positive, f to be negative, f to be positive. So what's the behavior of f? Well, here, notice where the derivative is positive, our function's increasing. Basically, that means we have a positive slope, right? So this is increasing. Here it's decreasing. And here again, it's increasing. And notice here, that's what matches this. So it's increasing, decreasing, and then increasing. And so where this is 0 is where we have our flat points, right? And so it's kind of nice to kind of look at it together. So let me zoom on in. So where the derivative is 0, we have our local max and mins. Where the derivative is positive, we have an increasing function. Where the derivative is negative, we have a decreasing function. And here, where again is positive, we have it being increasing again. And so it's just something good to look at and just kind of figure out there. Determine the local maximums of f if they exist using table 1. And here, this is how we used to define it beforehand. We found numbers and we tested above and below it to see if it was increasing and decreasing to figure out when a function went from increasing to decreasing. You did this vaguely before this class, just without derivatives. We found out that these are our local max and mins, right? And so here, our local, if a function goes from increasing to decreasing, we have a local max, right? So we have a local max at 1, at x equals 1, where the function value here is 5, where f of 1 is equal to 5, so that's the value. And then here we have a local min, because I'm going from decreasing to increasing. And this is how you were defined it before. This is the pre 181, and I just kind of wanted to connect it for you in a page. So pre 181 or pre calculus, this is how you define maxes, and that occurs here at 3. And then f of 3 here looks like -3. Okay. Any questions from any of this section?